Hello everyone. So today we are going to practice the mock test of the chapter D and F block elements. So let's begin. Okay, so we have our first question. Zinc has lowest enthalpy of atomization in the first transition series, that is from scandium to zinc. Because so you have to tell the reason that why in the first transition series, that is 3D series from scandium to zinc has lowest enthalpy of atomization. So you have given four choices. It has a fully filled d orbital with no unpaired electrons. It has smallest atomic radius in the series. It forms weak metallic bonds due to low nuclear charge, or it exhibits only +2 state. So if you see, the enthalpy of atomization depends upon the metallic bonding strength which is going to form due to the presence of unpaired electrons in the d outermost orbital present in the element, right? So zinc, if you see the electronic configuration of zinc has d10 configuration, which is going to be the stable one, fulfilled stable configuration zinc has. And due to the lower availability of unpaired electrons, or you can say no unpaired electron is present in the zinc due to d10 configuration, due to which the metallic bond it is going to form will be lower stable, right? So due to which its enthalpy of atomization will be lowest among the first transition series. Okay, so the correct answer is going to be that it has fully filled d orbital with no unpaired electrons, due to which it can't participate in the metallic bonding, and due to which the metallic bonding strength it form will be lower, so enthalpy of atomization will also be lower. So our first option is going to be our correct answer. Okay, let's move to our next one. So this question is that for a transition metal ion with 4 unpaired electrons, the calculated spin only magnetic moment in Bohr magneton is. So you have to tell that we have a transition metal, let's suppose transition metal ion in which 4 number of unpaired electrons are present. Okay, so you have to tell the spin only magnetic moment of that transition metal ion. So if you remember, the spin only magnetic moment formula is given by mu is equals to under root n plus 2, right? This is the formula in the Bohr magneton units. We calculate, using this we calculate the spin only magnetic moment for a transition metal ion. Okay, n here is representing the number of unpaired electrons present in that particular ion, and here already mentioned that n is going to be 4, right? So when you put here 4, it will become 4 times 4 plus 2 will be 6, and 6 times 4 will be under root 24, right? So under root 24 will have the value equivalent to your 4.9 Bohr magneton. How you can calculate? Under root 25 is 5. So under root 24 will be closest to 4.8 or 7 something. So 4.9 Bohr magneton will be the value of the spin only magnetic moment for the transition metal ion having 4 unpaired electrons in it. Hence our correct answer is going to be 4.90. Okay, and this 4 unpaired electron configuration is corresponding to basically chromium 2 positive having 3d4 configuration, where d4 is having 4 unpaired electrons. Okay, so B option is our correct answer. Okay, let's move to the next one. So this question is saying that which of the following statements about the magnetic properties of transition metal ions is incorrect? So we have given in the option some properties. You have to tell that which statement about this magnetic property of transition metal ions show magnetic property, and which statement is incorrect about that you have to tell. Remember, you have to identify the incorrect statement. Okay, let's read one by one. So the first one is diamagnetic substances are repelled by an applied magnetic field. Paramagnetism arises due to the presence of unpaired electrons. The orbital angular momentum contributes significantly to magnetic movement in the first row transition metal ions. Or ferromagnetism is an extreme form of paramagnetism. Now, if you see one by one, the first statement given is the correct statement because diamagnetic substance repelled by the applied magnetic field. In the applied magnetic field, diamagnetic substance actually repelled from it. Okay. Second statement is also our correct statement because paramagnetism arises due to the presence of unpaired electron in the particular element. If unpaired electron is present, that means it is going to show paramagnetism behavior. Now, if you see the fourth statement, that is ferromagnetism, the extreme form of paramagnetism, according to the definition of ferromagnetism, this option is also going to be correct because ferromagnetism is an extreme form of paramagnetism actually. So, only remain option is option third, which is saying that orbital angular momentum contributes significantly to the magnetic movement in the first row transition metal ions, which is going to be incorrect statement because for first row transition metals the magnetic moment is determined effectively by the spin angular momentum and not by the orbital angular momentum, and spin angular momentum given by mu is equals to under root n plus 2, right? So this statement given in the third option is going to be our incorrect statement, and hence this third option is going to be our correct answer. Let's move to our next question. So this question is saying that which of the following statements is incorrect regarding the stability of higher oxidation states in the transition metals. So you have to tell that we have given 4 statements regarding stability of higher oxidation state in the transition metals. You have to tell the incorrect statement. The statements are fluorine stabilizes higher oxidation states due to higher lattice energy or bond enthalpy. Highest oxidation state of manganese in its fluoride is +7 as in MnF7. Copper 2 positive oxidizes I negative to I2, that is iodide ion to iodine molecule, because CuI2 is unstable. Or oxygen can stabilize higher oxidation states better than fluorine in some cases. So you have to find out the incorrect statement. So if you see the first statement saying that fluorine is stabilize higher oxidation states due to the higher lattice energy or bond enthalpy. Okay, so this statement is basically the correct one because fluorine, the fluoride form with the transition elements, is going to be stable due to the fluorine higher lattice energy and the bond enthalpy value, right? If you see the third statement, which says that the copper 2 positive is oxidized iodide ion to I2 because of copper iodide is unstable. Okay, that is also going to be correct because copper 2 positive is actually oxidized I negative to iodide. That's why it doesn't form this copper iodide, this copper halide with the iodine. Okay, so copper doesn't form the halide with the iodine because copper iodide is unstable because copper oxidizes the iodide ions to iodine when it reacts with it. So this statement is also going to be correct. When you see the fourth statement that oxygen can stabilize the higher oxidation states better than the fluorine in some cases, this is also the correct answer. I mean the correct statement because oxygen can stabilize some higher oxidation state in the transition elements even better than fluorine in some cases of the transition elements. Okay, now the only remaining statement is the option second, that is the highest oxidation state of manganese in its fluoride is +7 as in MnF7. First of all, MnF7 does not form. Okay, and secondly the highest magnesium fluoride, manganese fluoride, the highest manganese fluoride oxide, that means in which the fluoride the manganese will show highest oxidation state, is going to be MnF4. where manganese is existing in +4 and not in +7. +7 is actually the highest oxidation state shown by manganese, but when manganese form fluoride, it show only the +4 oxidation state highest in its fluorides. Okay, so it form MnF4, not the MnF7 as given here, and +7 is achieved in oxides cases where manganese form Mn2O7 and not the like simple fluoride. Okay, so in the oxides of manganese attain its highest possible oxidation state, that is +7, but in the fluoride cases manganese achieve its +4 higher highest oxidation state as its highest oxidation state in the compound like MnF4, not MnF7. Okay, hence our correct statement statement is going to be, our correct answer is going to be option B, because we have to identify the incorrect statement. So B option is going to be our correct answer. Let's move to our next question. This question says that iron, that is Fe, exhibits a comparatively low standard potential value of M3 positive to M2 positive because. So you have to tell the reason. Why is it so that iron exhibit comparatively low value of E naught? So there are 4 reasons given. You have to select the correct one. Iron 3 plus is more stable than iron 2 plus due to the half-filled D5 configuration. Iron 2 plus has fully filled D6 configuration. Iron cannot attain a +3 oxidation state. Or iron 3 plus is paramagnetic while iron 2 positive is diamagnetic. So you have to tell that which reason is the correct reason for exhibiting the iron as a lower E naught value. So iron 3 plus is basically more stable than iron 2 plus due to the half-filled D5 configuration. This is our first reason. This is the correct reason because all other statements are incorrect. Iron cannot attain +3 oxidation state. That is absolutely wrong. Iron 2 positive as fully filled D6 is wrong. Fully filled D6 configuration is not fully filled. Fe3 plus is paramagnetic and Fe2 plus is considered as diamagnetic. This statement is also, which is given like this, that Fe2 plus is diamagnetic. So this is wrong. Only remaining statement is the first one, the first reason, the first option, that iron 3 plus is more stable than iron 2 plus because it attains half-filled configuration in the Fe3 plus. So why it show low E naught value, low standard enthalpy due to the extra stability of iron 3 positive due to its half-filled D5 configuration, which allows the iron 2 plus to iron 3 plus more. Okay, so this conversion of iron 2 plus to iron 3 plus is very suitable energetically. So it is energetically favorable due to why? Because D5 configuration is achieved in the Fe3 positive ion, and due to which it is going to show, or it is going to exhibit, lower value of standard electrode potential. So our correct answer is going to be our option first. Let's move to our next question. So this question says that the standard electrode potential, that is E naught for M3 positive to M2 positive for the zinc element. Zinc come in the first transition series. So for zinc element, the E naught is exceptionally high because, so you have to tell why it is so that zinc is show the higher E naught value for M3 positive to M2 positive. We have given 4 reasons. Let's see. So zinc 2 positive has a stable half-filled D subshell configuration. Zinc 2 positive has completely filled D10 configuration, making the electron removal difficult. Zinc 3 positive is more stable than zinc 2 positive due to the higher charge density. Or zinc exhibits anomalous behavior in the 3D series. Anomalous means the exception behavior in the 3D series. So I have to tell that which reason suits this answer or this statement of that standard electrode potential, the E naught for zinc is going to be exceptionally high. So basically, if you see the configuration, if we talk about the configuration, zinc 2 positive is going to have the completely filled configuration, that is of D10, which is discussing in the second option. right? So high zinc has exceptionally high E naught due to the zinc 2 positive configuration, which is D10, which is fully filled and stable. That means the removing of an electron will need higher energy from its orbital, and due to which it is having exceptionally higher E naught value. Okay, so the correct reason explaining the fact that why zinc is having exceptionally higher standard electrode potential value of M3 positive to M2 positive, because in the zinc 2 positive it is having D10 configuration, which is completely filled and stable, and due to which the removal of electron will need higher energy, so it is going to attain the higher E naught value. Hence, our correct answer is going to be the option B. Okay, let's move to the next question. Okay, so this is question number 7, and it is saying that the standard electrode potential, that is E naught for M2 positive to M, for the copper is positive, that is positive 0.34 volt, unlike the most other first row transition metals. Now, what is the primary reason for this observation? You have to tell. So, the E naught value for M2 positive to M for the copper element, which is a transition element, you have to say, you have to tell that why its E naught is positive, that is positive 0.34, unlike the other elements which are present in the first row of transition series, right? So if you remember, we have studied this, that, and if you observe the E naught value, standard electrode potential value of the first row transition metals, they are all in the negative sign, whether increasing or decreasing, but they are all in the negative sign. Okay. Only the copper is the element that is existing, or that is having only positive sign of electrode potential, standard electrode potential, right? So you have to tell that what is the primary reason behind this observation. The four statements given are hydration enthalpy of copper 2 positive ions, low sublimation enthalpy of copper metal, high sum of first and second ionization enthalpy of copper, low hydration enthalpy of copper 2 positive ions compared to the energy which is required for ionization. So you have to understand each and every option, then you can you can choose the correct reason behind this observation of positive sign of E naught value. So we have talked about the high hydration enthalpy of copper 2 positive ion, that is copper 2 positive ion show, right? So basically copper 2 positive ion hydration enthalpy we have discussed about it. So if you see and if you remember, the positive E naught, the standard electrode potential, that is E naught for the copper, is going to be positive due to the higher energy which is going to require for the copper solid to copper 2 positive conversion. Okay, so copper in the solid form to copper, directly to copper 2 positive in the aqueous form. Now this E naught which is going to be needed in this process, okay, standard electrode potential, that is going to be like high energy, okay, which is required to this conversion, right? And this is the sum of, like, E naught will be the sum of the sublimation energy, you can write it as delta sublimation H, plus the ionization enthalpy. Okay, sublimation energy for the conversion of solid to the gaseous, and ionization energy for the conversion of the solid, or you can say element, to the ionic form. Okay, so and this in this ionization energy, both ionization energy covers, like ionization energy 1 and the ionization energy 2. Okay, so basically what we are saying, that copper is having positive value of the standard electrode potential. Why is it so? Because it is going to like need higher energy to convert the copper solid to the copper 2 positive. That is going to be the sum of sublimation energy plus ionization energy. And ionization energy, we are talking about both the ionization energy, first and second. Okay, like copper to copper positive and copper positive to copper 2 positive. Okay, and it is not going to compensate by the hydration enthalpy that is going to be needed for copper 2 positive gaseous to copper 2 positive aqueous conversion. Okay, so copper 2 positive gaseous to the copper 2 positive aqueous is going to be the hydration enthalpy, right? So what we are saying, that copper to copper 2 positive conversion energy is going to be higher, which is going to be the sum of sublimation and ionization energy, and it is not going to compensate by this hydration energy. That's why the reduction of copper 2 positive to copper is less favorable, and that's why the standard electrode potential value of copper is going to be the positive one. Okay, so our correct answer basically is going to be the fourth option, which says that low hydration enthalpy of copper 2 positive ions compared to the energy which is required for the ionization is there. That means this doesn't balance the hydration energy and this energy which is going to required for the conversion of copper solid to copper 2 positive aqueous, which is the sum of sublimation and the ionization energy. And due to this reason, the copper is having standard electrode potential in the positive, unlike the most of other first row transition metals. Okay, so our correct reason will be present in our option D, that is lower hydration enthalpy of copper 2 positive ions compared to the energy which is required for its ionization, due to which copper will show the positive value of 0.34. That means the reduction of copper 2 positive to copper is less favorable. Okay, let's move to our next question. The question number 8, which is saying that which of the following compounds features a transition metal in the zero oxidation state. So we have given different transition metals in the options, right? You have to tell that which compound is having the transition metal oxidation state as 0. Okay, so we have given 4 choices: TiO2, FeCO whole 5, CrO4 whole 2 negative, or copper sulfate CuSO4. So if you remember, we have studied about the carbonyl ligand, right? So carbonyl, that is CO, is a pi acceptor ligand. Okay, so this is basically a pi acceptor ligand, and it is going to stabilize the lower oxidation state of transition metals or zero oxidation state. That means the transition metal, when form the complex with the carbonyl like ligand, which is going to act as pi acceptor ligand. Remember, we have seen the synergic effect we have talked about when the transition metal form the complex with the carbonyl ligand. Okay, so this is going to behave like pi acceptor, and due to which the transition element is going to be stable in the lower oxidation state or zero oxidation state in the presence of carbonyl ligand. Okay, if I tell you in detail, so basically when the carbonyl, when the metal form the bond with the carbonyl ligand, so the synergic bonding will occur in the metal carbonyls, and due to which the sigma bond and the pi bond both will occur. Sigma bond by the donation of lone electrons, that is CO, like this they are arranged, right? They are having here electrons, and metal is having the electrons. Okay, So what will happen? This carbonyl is going to bond between the metal, is going to bond is going to bond with the metal, okay, by the donation of lone electron of carbonyl carbon to the vacant orbital of the metal, due to which sigma bond form as the all ligands form with the metal, right? But the pi bond form here because the donation of electron from the filled d orbital of the metal to the vacant anti-bonding, the pi star bonding of the anti-bonding orbital of the carbon monoxide. So due to this, donation of this like free electrons or electrons from the filled d orbital to the vacant anti-bonding orbital of carbon monoxide, synergic effect happens and pi bond character will build, due to which the metal is going to be existing in zero oxidation state here when it forms the bond with the carbon or you can say carbonyl ligand. Okay, so synergic effect happens here and carbonyl will act as pi acceptor. When it bonds with the metal, metal will going to show lower, or metal will going to be stabilized in lower oxidation state or will show zero oxidation state. Okay, so that is only occurring here in the second case, right? So our correct answer is going to be option second, that is FeCO whole 5. Okay, let's move to our next question. Why does the stability of higher oxidation states decrease abruptly after the manganese in the first row transition elements? So you have to tell that in the first row transition elements after manganese, which comes in the middle, why the higher oxidation state stability decreases abruptly. You have given 4 reasons. The first is that increased nuclear charge makes it harder to remove the electrons. Fewer d electrons are available for bonding beyond manganese. The energy required to remove the additional electrons exceeds the bonding energy gained, or all of above. So basically, if you see one by one, the first reason given, that is the increased nuclear charge makes it harder to remove the electrons, this is going to be correct, right? Because after the manganese, the electron will start to pair up, right? And with each filling of the electrons, the nuclear charge will increase, right? And due to this, and also the 3d electrons is going to show poor shielding to the outermost electron, right? Due to which the increased nuclear charge going to affect the outermost electron and the size is going to decrease, and due to which the higher oxidation state is going to be less stable. Now if you see the second one, that fewer d orbitals are available for bonding beyond manganese, that is also going to be correct, because after manganese, filling of electron in the d orbital will increase. That means the pairing of electron will increase and there will be lesser available d electrons will be there in the elements for the bonding, for the metallic bonding beyond the manganese element in the first row. So this is also correct. Third, that energy required to remove the additional electron exceeds the bonding energy required. This is also correct, that the energy that you are going to require to remove the additional electrons from the d orbital is exceeding the bonding energy which is gained by the elements by forming the bonds. Okay, so this is also the correct reason for satisfying this statement that the stability of higher oxidation state is decreased. Okay, higher oxidation state means it can remove more and more electrons. So yes, it is going to be harder for removing the outermost electron from the d orbital after the manganese in the first row transition elements, due to the first 3 options given. Okay, hence our correct answer is going to be all of the above. Okay, option D. Okay, let's move to the next question. This question is that which of the following statements correctly explains the irregular trend in the first ionization enthalpy across the 3D series of transition elements? So you have to tell that in the given options, which statement correctly explaining the irregular trend which is observed in the first ionization enthalpy values across the 3D series of transition elements. The four options are: the 4s electrons shield the 3d electron more effectively as the nuclear charge increase. The 3d electrons shield the 4s electrons from the increased nuclear charge more effectively than outer electron shield each other. The increase in the nuclear charge is exactly balanced by increase in shielding by 4s electrons, or the 3d orbitals contract significantly, reducing the electron-electron repulsion. So basically you have to tell the correct reason behind the irregular trend observed in the first ionization enthalpy values across the 3D series of transition elements. So 3D electrons shield the 4s electrons from the increasing nuclear charge more effectively than the outer shell electron can shield one another. Okay, so this 3D electrons shield the outer 4s electrons from the nuclear charge, and this result in the slower increase in the ionization energy, okay, compared to the non-transition element. So that means our correct answer is going to be our option B. The 3D electron shield the 4s electron from the increasing nuclear charge, and it is going to be shielded more effectively than the outer shell electrons shield each other. Okay, due to which the ionization enthalpy trend is irregular in the 3D series if you compare in the non-transition elements. Okay, so option B is going to be our correct reason behind this. Let's move to our next question. Which element in the 3D series has the electronic configuration 3d10 4s1? So you have to tell that in this 3D series, which element has this electronic configuration of 3d10 4s1? The four options are chromium, copper, zinc, or nickel. So if you know the trend of the 3D series and the elements trend, if you have remembered that 3d10 4s1 is the outermost orbital, you have to identify which element it is corresponding to. Okay, so basically it is corresponding to the copper. Okay, because zinc is the last element in the 3D series, it is going to have 3d10 4s1, not 3d10 it is going to have 3d10 4s2, not 3d10 4s1. So copper is going to have 3d10 4s1. Basically it's expected as 3d9 4s2, but because 3d10 is more stable than 3d9, so its stable configuration will be 3d10 4s1 instead of 3d9 4s2. So the configuration 3d10 4s1 is corresponding to the copper element, hence our correct answer is option B. Let's move to our next question. Why is the copper positive ion is unstable in the aqueous solution? So you have to tell that why copper positive is unstable. It undergoes disproportionation to positive and copper. It forms an insoluble hydroxide precipitate. It reacts with water to release hydrogen gas, or it complexes exclusively with organic solvents. So you have to tell which is the correct reason that why copper positive ion is unstable in aqueous solution. So basically, disproportionation reaction copper positive undergo. So copper positive basically undergo the disproportionation reaction and becomes copper 2 positive and copper. Okay, here copper 2 positive is having higher stability in the aqueous solution. Also it is having a greater value of its hydration energy. Okay, that is why the copper positive is lesser comparatively stable than the copper 2 positive, and that is why the copper positive ion is unstable in aqueous solution and converts to copper 2 positive and copper, showing the disproportionation reaction. Hence our correct answer is going to be the first option. Let's move to our next question. In the first transition series, that is 3D series, the atomic radius generally decreases from scandium to copper. Now, what is the primary reason behind this trend? So you have to tell that in 3D series, if you observe the general atomic radius trend, it is decreasing from scandium to copper, like from the first element to the last element in the 3D series. Now, what is the reason behind this? Increase in the number of protons in the nucleus, poor shielding effect of d electrons, increase in the number of electron shells, or decrease in the effective nuclear charge. So in the 3D series, basically nuclear charge increases with the increase of each electron, because electron add with each successive member, the electron add in the inner d subshell. Okay, so d electron shield the outer electron poorly, and due to which the contraction in the radii happens. Okay, so that is why there is generally decrease in the atomic radius in the 3D series from scandium to copper observed. So our correct answer is going to be the option B, that is poor shielding effect shown by the d electrons. Okay, let's move to our next question. Which of the following conditions is most critical for the formation of homogeneous solid solution alloy between the two metals? So we have seen the alloy formation, right? So what is the most critical condition for the formation of the alloy, which is a homogeneous solid solution between the two metals? The four options are: the metal must belong to same group in the periodic table, the metallic radii of two metal must be within 15% of each other, both the metals must be transition elements, or one metal must be a lanthanide and other an actinide. So if you remember the alloy concept, that when the alloy formation happens, we have studied that one metal atom, uh, the one metal atom replaces the anothers in the crystal lattice in the formation of alloy. And alloy forms when the metallic radii of the component atoms are 15% of each other. This was the property we have to remember during the alloy formation, right? So our correct answer, correct reason is given in our option B. So correct answer is going to be our option B. Let's move to the next question. Which of the following statements about interstitial compound is incorrect? So we have given 4 statements. You have to identify the incorrect one regarding the interstitial compound. They are formed when small atoms like hydrogen, carbon, or nitrogen are trapped in crystal lattice of metals. They are typically stoichiometric with well-defined oxidation states of metals. They retain metallic conductivity despite the presence of non-metal atoms. Or they are chemically inert and often have high melting points. So, if you remember the properties of interstitial compound we have studied, we have seen the definition of interstitial compound, that it is formed when the smaller atoms like hydrogen, carbon, nitrogen filled or trapped in the vacant spaces of the crystal lattice of metal, right? So first statement is going to be the correct one. If you see the third one, that they retain metallic conductivity despite the presence of non-metal atom. This is also one of the properties of shown by the interstitial compound, that in the vacant spaces the presence of non-metal atom will be there, but still they retain their metallic conductivity, the interstitial compounds. Okay, so this statement is also correct. They are chemically inert and they often have high melting point. This statement is also correct due to the presence of strong bonding. Okay, so this statement is also correct. The only remaining statement is the statement second, which says that they are typically stoichiometric with well-defined oxidation states of metal. So interstitial compound because happens, or it builds because of the trapping of the smaller atoms in the vacant spaces of crystal lattice of metals. They are not stoichiometric. They are basically non-stoichiometric, and due to which they do not defined or well defined in their particular oxidation state of metal. They do not show particular oxidation state of metal. Example includes like titanium hydride having 1.7. So this is the formula of titanium hydride, which is an interstitial compound formed by the trapping of hydrogen atom, smaller hydrogen atom in the vacant spaces of titanium crystal lattice metal. Okay, so our correct answer is going to be option B. Okay, so this is how you can we have discussed some mock test questions. So you can also visit our website and practice the mock test of each chapter. Okay. Okay. Thank you.